Today we explore how a small sample can have a massive financial consequences in our processing. As you must be knowing, in processing plant involves a huge capital investment, yet their success often hinges on assays from teeny sample, and these sample must be highly representative, and the final sampling plan is always a compromise balancing theoretical rigor with the practical cost and difficulty. Now it's a again a matter of accuracy and precision. So let's talk measurement quality. Accuracy means how close we are to the true value. So it is about taking a reference point of true value, uh, and whereas precision means how consistent our measurements are. So once again, we can repeat that accuracy means how close we are to the true values, whereas precision means how consistent our measurements are. So ideally, we want both, but often we get clustered results that are either off target or scattered. So understanding this spectrum help us judge the reliability of our sampling results. So now coming to the mm, uh, PHE formula, which is supposed to be one of a cornerstone in sampling technology. So PHE developed a formula to calculate the minimum sample mass needed for reliable result. It depends on three key factors: the size of the largest particle, the acceptable error margin, and Ohm's characteristic. So this formula is a foundation in modern sampling science. So as we can see, the factors affecting minimum sample mass. Here, how those sample play out. First, particle size. Larger particle means exponentially larger sample mass. So if our particle size is higher, that means we have to collect a larger volume of sample. Second, acceptable error. A small error demands more material. It's very clear. And third is the ore characteristic, which is very vital and very important. Some ore require more sampling due to their mineral makeup. These three variables drive the math behind this PAG formula. Now, we took a real world example, and we see that how these things, how the things are applied with the help of a formula. So, for an ore with a 2.5 centimeter particle, a very small error tolerance of 0.005 and a K value of 257, the minimum sample mass required is 131 kg has been derived. So that's a substantial amount, showing how demanding high precision sampling can be a real world condition. Now, coming to the scoop size selection, the scoop size matters. For a top particle size of 50 mm, a 4 kg scoop is recommended. But if the top size is just 20 mm, a zero point 0.8 kg scoop is inadequate. These visual comparison highlight how particle size directly influences the physical tool we use for sampling. Now, coming to the summary of the understanding. To summarize, particle size dominate the sample mass equation. Precision requirement push the mass higher, and ore characteristic, especially mineral liberation, can dramatically affect the sampling constant. So these insights are critical for designing cost effective and scientifically sound sampling plan. In conclusion, small samples can make or break multi-crore decisions. Understanding the science behind sampling, especially PAG's formula, helps us avoid costly error and ensure that our assays truly reflect the ore's value.